Good morning, friends. We will start today ultrasonic testing. Ultrasonic testing UT is a powerful volumetric inspection method based on the propagation of acoustic waves. Such waves may be reflected or refracted at interfaces. Wave types. Frequency is measured in Hertz, and 1 Hertz is 1 cycle per second. While sound that audible to humans has a frequency between 20 and 20,000 Hertz. Ultrasonic waves used in UT have a frequency of 50,000 Hz to 5 MHz, 50 MHz. Most inspections are performed with test frequencies between 1 MHz to and 15 MHz. A wave is coordinated oscillation of atoms about their resting position that transfer mechanical energy while resting position of atom remains in the same place. Common mode of mechanical vibration, NDT, or compression longitudinal, shear transverse, Rayleigh surface, and lamp plate waves. The media for wave propagation. A medium must have density for a liquid or gas and or elasticity for solids to support an acoustic wave. The velocity of acoustic waves varies proportionally with elasticity, that is, bulk and shear modulus, mechanical material properties, and inversely with density. Some types of waves also require rigidity. Audible sounds is transferred as compression waves, which propagate through all material. Compression waves, which travel in the same direction as the atomic motion, are composed of compression plastic particles that are squeezed together and rarefaction particles that are pulled apart. The distance between the two equivalent positions on a wave, for example, two compression, is the wavelength. Acoustic energy propagates through homogeneous material at a constant velocity. Wavelength lambda for all types of waves is directly proportional to acoustic velocity v and inversely proportional to test frequency f. For example, 7.5 MHz traveling through a gold bar of velocity 3.25 km per second. So lambda equal to v by f. So wavelength equal to velocity divided by frequency. Don't have to go for so much as they gone here. You can directly convert it to 3.25 km per second. It is already written there. Or you can make it that and divide it by 7.5 because it is 10 to the power 6. And when you go for millimeter, you can get 10 to the power 6. So you get this in millimeter. No need for meter and all. So this is the first one, compression wave, direction of oscillation or direction of propagation is direction of oscillation and direction of propagation. The compression rarefication, there is only wavelength. The wavelength, one compression, one wavelength, compression to compression. Then C, the Rayleigh wave, or surface wave, elliptical, and then Lamb wave or plate wave, symmetrical, asymmetrical. Shear waves, Rayleigh waves, and Lamb waves can only propagate through a medium with an appreciable shear modulus of rigidity. That means they cannot travel in liquid. Particle motion on a shear wave is transverse or perpendicular to its propagation direction. Atoms with depth. Atoms in a Rayleigh wave travel in elliptical path whose displacement decreases with depth. So it can go up to 1 lambda max. This type of wave only penetrates to a depth approximately equal to 1 wavelength. Lamb wave are special wave mode that may only be generated in test object with free boundaries. These waves have an infinite number of modes for both symmetrical, longitudinal, and asymmetric or flexural displacement within the layer. Wave velocity. So compression and shear wave modes propagate with phase speed that varies with elastic properties of the medium. Shear wave velocity is approximately 50% of that of compression mode, whereas Rayleigh wave travel about 90% of the shear wave velocity. A wave velocity in steel decreases approximately 1% per 55 degrees centigrade rise in the temperature. So this is used as in the thickness gauge of high temperature objects. With, of course, when you are doing high temperature thickness gauging with a high temperature probe and high temperature cables and high temperature couplant. Transducer types: piezoelectric, electromagnetic, magnetostrictive, or capacitive. Piezoelectric materials, for example, quartz, lithium sulfate, an efficient detector. Barium titanate, efficient emitter. Emitter means accumulate an electrical charge in response to applied strain. They produce mechanical strain due to an applied electrical potential. Test equipment produces voltage pulses which the transducer converts into mechanical vibrations, and these vibrations are transferred into specimen near and far field. A piezoelectric element is a specific atomic lattice structure. Whether it will be preferentially produce compression waves X cut or shear waves Y cut, its central oscillation frequency is based on the thickness of the element, that is B by 2T. B is the velocity and divided by 2 of thickness. So central oscillation frequency. The waves produced by each point source constructively or destructively interact. Consequently, the distribution of sound intensities within the beam close to the face of the transducer varies dramatically. This is referred to as near field or Fresnel zone. Unexpected sound field intensity in the near field can lead to misinterpretation of discontinuity size. The length of near field effect varies proportionally with the crystal diameter and test frequency. The waves produced by each point source constructively or destructively interact. Consequently, the distribution of sound intensities within the beam close to the face of transducers varies dramatically. This is referred to as near field or Fresnel zone. Unexpected sound field intensity in the near field can lead to misinterpretation of discontinuity size. The length of the near field effect varies proportionally with the crystal's diameter and test frequency, and inversely with the acoustic velocity. So near field equal to d square f by 4b. So that is why it is directly proportional to the crystal diameter and test frequency d square f. So inversely to acoustic velocity v. Sound field intensity reaches a maximum at the end of near field, and it point mark the beginning of a far field, also called Fraunhofer region. Intensity decrease in predictable manner in the far field. It is decreased exponentially. Wave boundaries. Boundaries are the changes of acoustic impedance. Two boundaries, that is change in acoustic velocity. Recall that velocity is based on density and elastic properties. The amount of mechanical energy transferred varies inversely with the difference in acoustic impedance. Greater impedance mismatch causes more energy to be reflected and less to be transmitted. Use of couplant. Most use of couplant to transfer energy between the transducer and test object, or use electromotive force. In the case of electromagnetic acoustic transducers, couplant for contact and immersion transducer generally at room temperature liquid, water, glycerin gel, or honey, or grease. The acoustic mismatch is greater for an air specimen boundary than it is for a couplant specimen boundary. So amount of energy transferred is increased. For example, 99.99% of an incident sound field is reflected at an air quartz boundary, whereas only 68% reflected at a water quartz boundary. Employ matching layers to decrease acoustic impedance mismatch and increase energy transfer efficiency. So all this is the near field and the far field. Intensity of sound being sound field head has nodes, low amplitude, and antinodes, high amplitude. Within the near field. So there is high amplitude also and low amplitude also. Reaches a maximum at the transition point and then decreases in the far field. The packet of mechanical energy has a characteristic waveform, intensity, amplitude versus time, and the shape of initial pulse, as shown in figure 12.19, is governed by the electrical excitation waveform, for example, square or sinusoidal, provided by the ultrasonic testing equipment and by amount of mechanical damping assembled into the transducer to reduce the amount. For example, square sinusoidal provided by ultrasonic testing equipment and the amount of mechanical damping assembled into the transducer to reduce the amount of ringing. A mathematical operation called Fourier Transformation, also referred to as first Fourier Transformation, used to graphically observe the spectral amplitude, that is frequency components of a waveform expressed as a amplitude versus frequency. With this peak, often 50% of the maximum minus 6 dB, 50% of maximum or minus 6 dB is known as bandwidth f2 minus f1. Attenuation of waves. The pulse waveform distorted as it propagates through the specimen. This is known as pulse broadening. Attenuation is caused by absorption, scattering, and their relative effects vary with material properties and test frequency. Higher frequency offers improved inspection resolution, but higher frequency components of the pulse are attenuated more quickly. Lower test frequency may require to fully penetrate a large specimen or to decrease the amount of scattering due to boundary reflection, such as crystallite grain boundaries within a coarse grained specimen material, internal porosity, or material changes within a composite. As the sound field attenuates, it also increases the diameter with distance, that is diverge in the far field. Increased test sensitivity is possible when a greater amount of sound energy is focused onto discontinuity of interest. The rate of divergence increases proportionally with the acoustic velocity of the medium and inversely with crystal diameter and test frequency. So sin theta by 2 equal to k lambda by d, kv by df. So it is proportional with velocity and inversely with crystal diameter and frequency, kv by df. The pulse will have an average velocity in spite of some component traveling more quickly or slowly. The variety of individual velocity, that is phase velocity due to their unique frequency, is to peak broadening because faster wave will return and echo more quickly than slower waves. When the pulse travels through a dispersive material, which tends to preferentially attenuates higher frequency component, the inspector may observe the decrease in acoustic velocity. Dispersion of waves. Lamp waves in particular are affected by dispersion, which means that wave packet velocity varies with test frequency as well as the density and elastic constant of the medium. The pulse will have an average velocity in spite of some component traveling more quickly or slowly. That variety of individual wave velocities, that is phase velocities due to their unique frequency, lead to peak broadening because faster waves will return to echo more quickly than slower waves. The pulse travels through a dispersive material tends to preferentially attenuate higher frequency components. The inspector may observe the decrease of acoustic velocity. Practitioners are generally concerned with two phenomena. When a sound field encounters a discontinuity reflection by which some incident sound pressure rebounds back towards the source, and diffraction by which discontinuity boundary itself oscillates and acts as a low multitude point source of acoustic energy. Due to the many factors that affect discontinuity echo amplitude, it is often difficult to determine the precise size of discontinuity. Large reflectors perpendicular to second field are ideal, while actual discontinuities may be not discontinuities may be rough, spherical, tilted, and return less pressure. For example, casting pore may be essentially spherical, whereas inadequate weld fusion is likely to be aligned with the bevel rather than parallel to the external source surface. Normal versus angle incident. Acoustic energy may be introduced in variety of angles with respect to external surface of the specimen. Waves Normal incident waves perpendicular to the exterior by convention and said to propagate at 0 degrees. Angle incidence is sometimes desirable to induce shear waves. Insonify it or direct the sound beam towards the angle that provides maximum reflection from angle discontinuities. Avoid specular reflection from the test object's front surface. Induce surface waves, induce Lamb waves, or diffracted waves. Snell's law. Reflection and refraction, both of which involves of direction change of transmitted wave, occur with sound field encounters a boundary at the angle of theta 1, as shown in figure. The angle of reflection is always equal to angle of incidence, while the angle of refraction varies with relative acoustic velocities on both sides of boundary. Faster compression waves refract at a greater angle than the slower shear waves. Mode conversion occurs at angled boundaries. The faster compression waves refract a greater angle than slower shear waves. Mode conversion occurs angle boundaries, which means more than one wave mode may transmitted. So refraction angles are calculated using relationship known as Snail's law. Sin theta 1 by theta 2 equal to V1 by V2. Critical angle. Inspection generally uses single wave mode. So Snell's law is also useful for determining the minimum and maximum incident angles that produce only shear waves within the test object. Compression and shear waves will both be present at angles less than the first critical angle, making signal interpretation challenging. The first critical angle is the incident angle where the faster compression wave component is no longer present. In other words, theta compression greater than equal to 90 degree. So this refracted compression will be outside, just outside. Then it is first critical. When shear wave go outside, refracted shear. So when refracted compression go outside, first critical angle. When refracted shear go outside, that is second critical angle. That's the first critical angle at a water aluminum interface with this velocity, and the incident sound field is originated 13.59 degrees of perpendicular. So sin theta 1 by theta 2 equal to V1 by V2. So just keep it in kilometers. No need to change. So sin inverse sin 90 1.48 divided by 6.3. So that is 13.59. For water aluminum interface. So for what for perspex and steel interface, it will be around 27 degrees. You can calculate. Use of wedges. Wedges are common on conventional single angle transducers, for example 45, 60, 70. The wedge angle for single angle probes is fabricated based on Snail's law to produce a shear wave within the test object at a desired angle. So there is one angle only. Velocity and consequently the angle will change with temperature. PIOT system can electronically sweep the sound field through a range of angles in what is known as sectorial scan. Focus the acoustic pressure at desired depths within the near field and scan an area without moving the probe as in a linear scan. So we'll stop here first.